Χριστίνα,
Έλα, Τάκη.
λοιπόν, σου έχω γράψει ένα chat. Μπορεί να το δεις λίγο?
Οκ.
Λοιπόν, ό,τι κάνουμε τώρα φαίνεται και στο YouTube.
Οκ.
Εντάξει. Λοιπόν,
Ναι, ναι.
εγώ τώρα θα κάνω live meeting και θα πάρεις εσύ τη διαχείριση. Οπότε όσοι περιμένουν πρέπει να τους κάνεις εσύ admit.
Εντάξει.
Λοιπόν, κάνω λίγο live εγώ και λέω στη Χριστίνα να γίνει assigned ο host, εντάξει.
Μμμ. Δεν ήρθε κάτι. Μ' ακούει? Α, εδώ είναι 6 participants. Ναι, οκ.
Εντάξει, Χριστίνα, πήρες τα δικαιώματα.
Τους βλέπω, ναι.
Οπότε, όποτε θες εσύ θα τους κάνεις admit. Εντάξει.
Τους έκανα τώρα.
Ωραία. Λοιπόν, δεν ξεχνάτε τα μικρόφωνα ανοιχτά. Κάνεις τη διαχείριση εσύ, στέλνετε το YouTube, κάνεις συνεγγραφή.
Οκ.
Άντε, καλή επιτυχία.
Ευχαριστούμε. Ξεκινήσουμε. So we can start now. Good morning to all. My name is Christina Azeri. I'm a marine chemist researcher at the Hellenic Center for Marine Research. And I'm very happy to welcome you all here in the room and also our participants online. Many people are still joining. And I would like to express a great thank you to our speakers, with whom who will share with us with some very valuable information in a while. So this workshop, which is dedicated to approaches for measuring and identifying microplastics in the marine environment, has been organized by Argyro Adamopoulou. Argyro is a co-worker with us, a collaborator. She just obtained her PhD a couple of months ago, working on the field of floating microplastics and degradation patterns in the marine environment. And now she has also received a grant for early career scientists from the Eurocians Euromarine initiative to further work on this subject. And under this Harm-Plast project, she has organized today's workshop. So Argyro, the floor is yours, and good luck.
Good morning from me as well. Thank you all for being here, present and online. Before we go through the Harm-Plast and what it stands for, Harm-Plast stands for Harmonized Spectral Analysis for Environmentally Weathered Plastic. And let's meet the team. The team is Win from Moore Institute and in USA and creator of Specy. Then is Mariana from VLIS and Giuseppe from SNR, and all three will give presentations later on at the workshop. Well, once plastic enters the environment, due to weathering, it fragments into smaller items. We have the macroplastics, the mesoplastics, and then the smallest ones being the microplastics. Today's presentation will focus on the microplastics being bigger than 300 micrometers because the sampling was secured with Mantanet. Monitoring MPs at the worldwide level has been challenging due to the wide range of methodologies that have been applied for sampling, extraction, counting, and polymer type identification. And research has proved that estimating microplastics only with microscopy can yield to false positive or false negative results. So why is it important, the polymer type identification? Because it's actually we use FTIR for the polymer type identification, and FTIR produces a spectrum, which is the fingerprint of the polymer. Then at the instrument, we have the libraries, the commercial libraries of the instruments, which are actually matched with the spectra we are analyzed, and then we have the heat quality index, and finally the identification of the plastic. The weathering process alters the polymer spectrum compared to the spectral signature of their virgin counterpart, making it challenging to identify the samples from the environment. Therefore, it's necessary to use common, harmonized, and weather libraries for polymer type identification to improve data consistency. So what we see here at the bars, we see that from 2010 to 2020, the publications on plastics and microplastics in general have increased exponentially. With purple, you see the publications on microplastics. And then also we see that the sampling effort worldwide in the ocean and in the sea has also increased. But our laboratory is in sync on microplastic chemical identification, and what do we know about environmental microplastics, weathering status, and fragmentation? So what in Harm-Plast, basically we do an interlaboratory comparison, which we identify the very same plastic items from macroplastic, mesoplastic to microplastic of basic polymer types like polyethylene, polypropylene, polyester, and other types that we find in the environment. Specifically, we identify the items first. The first identification occurred at HCMR using an Edgeland instrument, and then the second identification of the same items occurred at SNR using a Bruker instrument, and the third identification occurred at Vlies Institute using a Perkin-Elmer FTIR. What are the goals of the Harm-Plast? Are to identify and validate the polymer type, to optimize the spectra, and to estimate the weathering status using the carbonyl index. Then once this is done, we will generate spectral libraries of environmentally weathered plastics that will be uploaded at OpenSpecy. For those of you who are not familiar with OpenSpecy, Wayne will later on explain what OpenSpecy is. And then we will also add the carbonyl index as metadata in OpenSpecy. So today we will present only some preliminary results of the Harm-Plast. So we will have results only between comparing the two instruments of Edgeland at HMR and Bruker at SNR. And by the end of spring, we'll have also from Vlies. So the first results, we say that comparing the polymer type identification differences between the instruments, so that the identification difference between the instruments increases as the size of the plastic decreases. So we see that for macroplastics, that are the biggest particles, we had 6% identification difference between the laboratories. And we had polymer types of polyethylene, polypropylene, and polystyrene. Then for mesoplastics, the identification difference increased to 7% for polyethylene, polypropylene, and polystyrene. And for microplastics, which are the smallest ones, the identification difference between the instruments was 15% for polyethylene, polypropylene, polystyrene, and other polymer types. So as we go smaller, as the items become smaller, the variety of the polymer types also increases. So the differences between the two laboratories were observed for spectra that had heat quality index between 60% and 80%. And why this could be, the reason for that could be that the spectra were weathered, and therefore the matching was not with the libraries, was not above 80%. So this is a problem. That's why we need weather libraries. Then, as I said before, the weathering process alters the spectra. So what we see here at the graph in green, we see a pristine spectra of polypropylene. And then with blue, we see the very same spectra of polypropylene, but the degraded one. In the orange box, what you can see is the creation of a little peak, which is the carbonyl peak, which presents the degradation of the polymer. There are various carbonyl indexes used, not only from environmental sciences, but also from scientists that study polymers, and they are doing experiments. But specifically for our work here, for Harm-Plast, we use the carbonyl index, which is the specified area under band, the SAUB index, which is considered from the literature as a robust index, especially for environmental data. So what we observe here, here we see the carbonyl index estimation for polyethylene. We only kept the fragments, so microplastics have different shapes, but in order to compare the carbonyl indexes, here we have only the shape type fragments. And then in blue, you see the data from HCMR, the raw data of polyethylene the raw carbonyl index data. And in orange, you see the data from SNR. So what we observe is that the carbonyl indexes, when we use the raw spectra, are significantly different. So the mean value for HMR is around 0.9, whereas for SNR is 2. So we'll have a total different, for the very same particles, we have a total different picture depending on the instrument we use. We perform the same for polypropylene, microplastics, again, only for the same type of fragments. And likewise, the polyethylene, we observe that the carbonyl index values originating from the SNR had double, the mean value was double than the HMR. Therefore, if we would use the raw data, we wouldn't be able to have a conclusion of the weathering status of the items from both instruments. So what we did is we did spectral pre-processing, and we performed two types of baseline corrections. Here we see the FieldPix baseline correction. So the little graph is the raw data that we saw before. Then we perform the FieldPix baseline correction, and we have the new carbonyl indexes, the new calculations based on the corrected spectra. And what we see here is that the differences between the two laboratories are not anymore significant. And the mean value for HMR is 0.7 and for SNR is 0.8. Same goes for the mod polyfit baseline correction, again for polyethylene fragments, where again the difference between the laboratories was decreased. We performed exactly the same baseline corrections for polypropylene. And again, when we perform the baseline correction, the difference between the laboratories is not significant. This is very important here because when we calculate the carbonyl index, we are supposed to have one value from all instruments. So to reach to some conclusions, the validated spectra from the three instruments used as weathered spectral library at the open access Open Specy will increase the heat quality index, the library harmonization, and data accuracy, quality improvement, and comparability between the laboratories. Then the carbonyl index values of raw spectra for polyethylene and polypropylene are statistically significant between the two instruments. Also, the carbonyl index can only be used for polyethylene and polypropylene. And also polyethylene and polypropylene account for about 80% of the microplastics we find in the floating in the environment. So both baseline correction methods improved the comparability of carbonyl index values between the laboratories. And then we aim to the creation of an open access carbonyl index data set of environmentally weathered microplastics. Why it's so important, the correction, is because at the end, the Open Specy, the end user, like any of you, could actually have the spectra from your sampling campaign and then upload it up the Open Specy. Then your spectra will be matched to a weather spectra. So you will increase your heat quality index and avoid mismatching or low percentages. And then with the correction, we'll manage to have as a metadata also the weathering status of the microplastic, which has to be one value, not two values if we use the raw spectra. So that's it, some preliminary results, and hopefully by spring we'll have more. And it's quite interesting, and we're very happy so far. I would like to thank Zeri, Christina, ΕΛ.ΚΕ.Θ.Ε, and George Budas for their help and support for all this work. And of course, the rest of the Harm-Plast group, and all of you for being here and for the attention. Thank you. The questions, they will be at the end of the workshop for all the presenters. So actually, if Giuseppe can come to continue with the presentations.
Sit in your place?
Yes, I will move. What do you...
Sorry, do you want the... No, you can try the PowerPoint.
PowerPoint.
Because there are some animations.
Okay, super.
Okay.
You can just...
Okay, good morning. Kalimera, thank you for the invitation. It's really a pleasure for me. Greece is my favorite country in the world, so it's always amazing to be here. I'm Giuseppe Suaria. I'm a senior scientist at the Italian Research Council, specifically for the Institute of Marine Science in Lerici, in the northwest of Italy. So Arghiro already explained about the project we are collaborating with. It was amazing. It was first time for me also to see the results. So it's great result. Thanks for sharing those. I will be presenting you the results of a few other projects we did on the harmonization. I actually changed the title a little bit, so sorry for that. So I will, because the workshop is about harmonization, I will be mainly talking about harmonization. So, but why do we need to harmonize plastic measurements? Well, this is quite an interesting slide. So if you take just two random papers about microplastics in wastewater, and you go to the results section, and you see that the authors basically reported about 0.266 microgram of microplastics per liter in wastewater effluents. And then you just take a paper about microplastics in human blood, you go to the results, and you see that the authors found 12,500 micrograms per liter of microplastics in human blood. So what does this mean? Does this mean that in our blood we have orders of magnitude more microplastics than in wastewater? Well, of course, it's not the case. This is all about analytical tools, analytical protocols, and huge differences in the protocols used by these two different studies. And so basically the data we are reading are not really accurate. They cannot be taken as they are. Our ability to correctly quantify microplastic content in different matrices is not replicable, is still not replicable. But what is the final goal? So the final goal probably is to understand better the cycling of plastic through the ecosystem, including us, including humans and organisms. But so we have to replace basically all these question marks with numbers. So we need to have a better understanding of the plastic cycle in the environment. We do have some estimate of the input of plastic from land into the ocean. We do have some estimates about the amount of plastic floating on the surface of the ocean, but then we have all these question marks in all the other compartments. And so this should be our final goal, is to basically replicate what we did with the carbon cycle and with the cycling of all other elements in our ecosystems, where we basically were able to replace question marks with numbers in the global fluxes. And so we can better understand if in the end our mitigation policies will be effective or not. But what is comforting, you're probably familiar with the concept of the missing plastic sink, this mismatch between what we estimate to enter in the environment and what we find into the environment. Well, the carbon community was having exactly the same issues when they were working on it in the 1990s. They also had a missing carbon sink that they didn't know where was it, and in the end they managed to figure out what was happening and to have all this nice idea of the global carbon cycle. So this is the goal for plastic, and this is basically why we need harmonization urgently. But the main difference between carbon and all the other elements is that plastics are not just a single molecule or a single atom or a single element. Plastic is just a collective term that it actually means nothing. It's just a collective term that encompasses hundreds and hundreds of different polymers with thousands and thousands of different additives, which are used in thousands of different applications and different products, and they come in many different sizes, on which we still do not have an agreement. And then all different morphologies, colors, and then toxins and chemicals. And so it's very complicated to try to harmonize, to find a protocol that works well for this huge variety of materials. And this is basically the main challenge, and this is the main reason why we still do not have achieved harmonization in the plastic field of research. And this was actually also the main driver behind this big Horizon project. It was called EuroQ-Charm. Argiro asked me to present something about it. It was a big Horizon, a 2 million euros project that was focused on improving the harmonization in monitoring plastic pollution. And this was done basically by performing a huge systematic literature review. We've been reviewing thousands and thousands of papers systematically about plastic pollution. And then the idea was to extract these reproducible analytical pipelines, so to break down every protocol into this RAPS. And to score these reproducible analytical pipelines according to their TRL, so their TRL scale. So how much is the technological readiness level scale? So how much this section of the protocols were actually replicable and reproducible. And then we did an interlaboratory comparison study between many laboratories in Europe, and finally some recommendations were published to the main stakeholders. Just going a little bit more into the detail, this is the systematic review we performed. We extracted a total of more than 3,000 articles. Then these were cleaned up and screened, and then 2,500 were retained, more or less. 1,800 were retained. In the end, they were divided into different compartments: solid, water, biota, and air. And then these all the protocols for all different compartments, they were divided into these 6 steps: survey design, sample collection, sample preparation, analytical detection, plastic quantification, and data reporting. And each one of these steps for each one of the paper were scored according to the TRL scale. So the whole goal for this was basically to try to have a better idea of the huge diversity of the protocols that were being used by the scientific community, and try to recommend some of the most powerful protocols to the community. So, for example, if we apply these to floating microplastics, which is basically where the field of research started and what most people were doing for many, many years, well, we can conclude that basically major sources of error are still associated to each one of these steps, and I will briefly go into the detail of this in my presentation, focusing only on floating microplastics. Then, of course, you can apply these to all other compartments, biota and human blood, or sediments, or whatever. But the key message is that most of these steps, they still have a very low technological readiness level. So they still cannot be really recommended, because they cannot be considered reproducible, and so they cannot be recommended for global scale monitoring programs. For instance, even before collecting samples, we have major issues with survey design. So how do we choose where to place our sampling station in the marine environment? Are we monitoring, or do we have an hypothesis? How many samples shall we collect to correctly represent the concentration of plastics in a given area? Shall we perform repeated transects? What about temporal trend and small scale variability and repeatability of our samples? Is it better to randomize completely our sampling in our study area, to collect single sample or replicate samples? How many replicates are needed to have representative results? So these are all major questions that are going to affect our result and basically the representativeness of our results. And most of these are still unanswered. And then we have sampling methodological, a huge variety in the sampling tools we can use. We can use Newton net, Manta nets, Bongo nets, multi-nets, and this is mainly for large microplastics. And then if we want to sample smaller microplastics, then we can use Niskin bottles or bulk water sampling, in situ pumps, sediment traps, underway pumps, and filtering systems. So there's really a huge variety of methods that people are using right now, and harmonize this is extremely complicated. But I have to say that this was one of the main achievements, is that if we divide large microplastics from small microplastics, we are already making a huge step forward, so in recommending monitoring tools. So the uncertainties in the measurement of microplastic concentration, they come from sampling error, instrument error, and laboratory analysis error. So just think that most of the floating microplastics analysis right now are still made, even in our laboratory, are still made with visual sorting. Visual sorting has an extremely high subjectivity, and two operators will spot, identify, and count completely different things. And we try to compare the count on the same samples made by two different persons, and they are not comparable at all. So if we are quantifying samples, microplastics using visual sorting, then we are introducing already a major source of error into our study. Then there are uncertainties associated to the volume estimation with the plankton net. We performed a very small experiment in a previous project. It was called Baseman. It was a JPI Ocean project. And we collected two samples in parallel with two different nets, a Houston net and a Manta net. And then you can already see by naked eye that they collect completely different amount of plankton. And then if we report our microplastic counts in unit area, so in atoms per square kilometer, for instance, we will have obvious differences in our microplastic concentrations here. So how much can we trust the data that we are reporting then in the end? A major advancement was made recently in 2023 by the Japanese government. The Ministry of Environment in Japan, they produced and published these very useful guidelines for harmonizing floating microplastics monitoring. And you can find some very nice information into this report. If you are interested, I really recommend you to read this. For instance, they did a lot of experiments. They did, for instance, they compared the tow duration, 10 minutes and 5 minutes, and two smaller, shorter throws by 5 minutes each. You can see you can have some very different results. So what is the right duration for towing a manta net? Then the position of the net can also affect the concentration of microplastics. Either if we sample from the port side or the starboard side, the downwind side. Then they also measured the immersion depth of the net, and they saw that the immersion depth of the net during a troll will change a lot. So if we want to compute the volume using the net dimension, then we can make a big error here, because the immersion depth will go from 30–40% up to 70% at the end, after 20 minutes of troll. And then the effect of salinity, for instance, affecting the concentration of microplastics. This is basically the tide cycle. So the moment of the day in which we are sampling can also affect greatly our result. These are some of my data, and basically they show that if I compute the troll distance, so how long was my net troll, using the three most commonly used method, with the flow meter, with the speed and time, and with GPS, start and stop position, I have different results. So, and these will be reflected into my concentration in microplastics per volume or per area. And so, and the result is really great. It's almost a double. This, of course, has huge implications, because are gonna halve basically my microplastic concentrations. Also, sea state, some guidelines, they suggest to record the sea state, and it is clear, this is still from the Japanese report, this is clear that with the microplastic concentration is related to the wind speed. So the higher the wind, the lower the concentration. This is because microplastics will be resuspended in the water column. So we should always take this into account and perhaps develop some correction factors and correct our data accordingly. And then, okay, we collect our sample. We have all these huge sources of error before, but then we bring it to the lab, and then how do we extract? We do visual sorting, we extract of the particles, and then we have to analyze them with FTIR, as Agargiro said. Well, how do we choose a representative subset of particle to analyze? Are we sure that we are randomizing these in a proper way, that we are sampling like a representative variety of our particles? Here, Harm-Plast, you already saw this. I'm not gonna talk more about this. We will learn a lot about this project. But yeah, other issues. So which software should we use? How can we improve harmonization? This is the goal of the Harm-Plast project. Match rate, which libraries are we using? We will learn more from Win later, databases and so on. But then it's just to stress that the new state-of-the-art FTIR machines, they do mapping, and so they are a great advancement in the field because basically they remove the human bias. So you don't have to visual sort the sample anymore. The machine will analyze everything on a filter, and so this can really greatly reduce the error in our analysis. And what is interesting here is that when you use this state-of-the-art FTIR, the mapping methods, most of the particles are actually smaller. The vast majority of the particles are smaller than the mesh size we traditionally use. So, and that is why we should recommend two completely different protocols for large particles and small particles. And then other sources of errors. How do you measure a particle size? So we all often read in the papers like the size of these microplastics, but there are many different ways of measuring the size of a particle. Are we using the fairest diameter or its longest dimension of the perimeter or the spherical diameter and so on? So also these should be harmonized because it's really important and quite critical when talking about irregularly shaped particles. And then just a couple of slides about fibers. Argilo, please stop me if I am being too late, probably already over time, but 2 minutes. So fibers, this is a topic of research I've been spending a lot of time recently. If you dig into the literature, fibers, they always account for more than 70, 80, 90% of all the particles, if you can see this review. So most of the microplastic studies they report fibers, they actually report a majority of fibers. So most of the microplastics are actually fibers. But I think that they are completely different from the traditional microplastic fragments. They have different sources, behavior, and solutions and impacts. And so they should be, in my opinion, considered as a distinct class of contaminants. And also, if you do procedural blanks in your laboratory, you will mainly find fibers. So there are also huge problems associated to contamination. And what is more interesting is that from a recent publication from our lab, we demonstrated that the majority of these fibers are actually not plastic at all. They are made of cellulose, they are cotton or other cellulosic fibers or wool. Just a small minority is microplastic fibers. And this evidence is appearing more and more in the literature, in the atmosphere. Most fibers are made of cellulose. In fresh water, they are made of natural fibers, and so on. So the assumption that most fibers were microplastics has probably led in the past to huge overestimation of the concentration of microplastics in the ecosystems. And again, this paper published in Science, you go in the supplementary, you say the majority of the particles these authors considered as microplastics in the seafloor, they were actually microfibers. So mostly they were probably not microplastics at all, over 90%. So shall we consider fibers for monitoring? Do they need dedicated protocols? Probably yes. Anyway, so I'm finished. These are my last 2 slides. These are the main output of the EuroQuestion project, and we need harmonization in all the steps, especially when we talk about large microplastics. There are still huge sources of error in the quantification of these particles. For small microplastic, if we apply the state-of-the-art mapping methods, it's easier to harmonize these because regardless of how we collect the samples, the analysis will be always the same, and so it will be more reproducible because there will be no human error. It will be made by machine. And of course, but we need to harmonize how we report our data. Just very quickly, another Horizon project, we try to remove human bias from the whole procedure by developing a sensor. Currently working on this. It's not really working very well, but promising results. So just in conclusion, we need to develop urgently a roadmap to harmonize our sampling and analytical protocols. The automated mapping is promising, and it's very important to quantify the smaller microplastics. Smaller microplastics cannot be reported using the methods we've been using so far. Contamination is also very important. And all these issues are critical to develop European and global monitoring programs like the IMDOS program. I am in the steering committee of this. It's basically trying to push further the harmonization on the global scale, because all countries in the world will need to report and measure and just to see if the policy we are implementing are effective or not. So thank you very much. Sorry for being late.
Okay. So good morning, everyone. I'm Nicoletta Viga, and I'm also a member of the Microplastic and Marine Litter team of the Hellenic Center for Marine Research. I'm going to talk about some insights and approaches on microplastics detection in biota and sediment samples. Of course, I guess we all know what microplastics are. That's why we are here. Are widespread environmental pollutants accumulating in aquatic and terrestrial ecosystems. Their detection in seabed, sediment, and in biota is very important in order to understand the impact on the organisms and the ecosystems. Actually, a recent review reported that more than 822 marine species have been ingesting microplastics between the period of 1972 and 2021. Actually, Science Journal published the first publication in 1972 on microplastics in biota and sediment on the Sargasso Sea. Although many steps have been done, there are still many things to do in order to improve our methodologies. There are many advancements to be done and challenges in order to improve our practices. And that's why recently there have been published many reviews on the topic. Many people are trying to compare and to gather all these techniques and methodologies in order to improve ourselves. As microplastic research is a new topic, there are many challenges and many problems, as Giuseppe presented also earlier on water samples. I thought that I included most of the basic challenges, but finally I didn't, because also Giuseppe had a lot of more, added a lot of more challenges. However, I will try to also cover some of the main challenges we face in biota and sediment analysis. So we have many different methodologies on sampling selection in biota and in sediment. Many bioindicator species, different tissues to focus on, the whole tissue or specific tissues on the organism. Also, concerning microplastic separation, there is the visual separation of microplastics or digestion in order to get rid of the organic material with different treatments. In sediment, you can do some pre-processing with peroxide or sieving or density separation to separate the microplastics from sediment with different solutions. When you want to identify and quantify the microplastics, there are also many different ways. The traditional hot needle test, visually with a stereoscope, stereoscopic techniques like FTIR, micro-FTIR, Raman spectroscopy, or thermal analysis, pyrolysis, DCMS, etc. There is also a problem with expressing units, as Giuseppe also referred earlier, I think, which is very difficult then to compare our results. Some people, for example, some laboratories, some studies show that they present their results as microplastics per individual, others microplastic per gram. In sediment, you can see microplastics per volume or per square meter or per per kilo of sediment, etc. And this makes it really difficult to compare. We distribute microplastics in different size classes. So again, it's difficult to compare. And some of the above techniques have some detection limits. You cannot go in microplastics smaller than 300 microns, or in pyrolysis, for example, you cannot have the quantification of microplastics, but just the mass of the microplastics. We have a huge problem with airborne contamination. We have to protect our samples very well from the microfibers that are found in the working environment or on our clothes. We have, again, a standardization issue. Our protocols are not yet globally harmonized. And of course, we don't have established threshold limits for assessing the good environmental status concerning the microplastic ingestion. So in our lab, we try to tackle some of these issues all these years. We started in 2013 working with microplastics on the sea sediment, on the beach sediment. And then soon after, in 2014, we entered this world of microplastics in biota. But the first pictures we had were like this, which means with a lot of noise, with a lot of microfibers, dirty samples. So we realized that we had to do something to change our methodologies and to protect our samples from airborne contamination. So some of the measures we took back then was to work in isolate places, to cover samples with aluminum foil, to use in every step blank samples, to wear specific coats, etc. More precaution measures were published in this publication of 2016. The next years, we tried to standardize our techniques and methodologies with the stereoscope to visualize and to try to detect suspicious particles as microplastics, and then to identify the polymer type with the micro-FTIR. And this led us to the first publication in Greek for microplastics in biota. Later on, in 2018 and 19, the discussion on bioindicator species started, which I think it's very important because suitable bioindicator species are used to monitor the presence and the effects of microplastics in different habitats. So you need to have sufficient information for the species to know their habitats, to know their home ranges, their feeding behavior, and depending on the organism you choose, if you choose a wide spatial distribution organism, then you have information for a big scale area like the Mediterranean Sea, or for a smaller area, you need to have sessile organisms. In order to link this information with human health, you need commercial organisms that are edible from humans. And of course, you want documented microplastic ingestion, which is nowadays very easy to find because most of the species have been found with microplastics. And all these were included in these very important publications. In 2020 and 2021, we participated in two interlaboratory studies. One was under the framework of the Marine Strategy Framework Directive about sediment and water samples, but here I will just present the sediment. And the next one was under the Plastic Buses MPA's project on marine biota. Why it's important to participate in these exercises? To validate our methods across the different labs that participate in the project, and to find the optimal method to work and to conduct harmonized monitoring. In the first case, 5 laboratories have participated, 2 samples each laboratory, 5 different polymer types with microplastics that we created ourselves, as you cannot find them in the market, 5 different methods, each lab its own method. And the results is that we all suffered from underestimation of microplastics. The recommended protocol was sodium chloride to separate microplastics from sediment. It was very difficult to obtain clean natural sediment as a reference material, and the FTIR was really helpful and important for our results. In the second case, 4 labs participated. 2 different species, again, 3 polymers created by ourselves, and 2 methods, digestion methods, were tested. In terms of recovery rate, of alterations of the plastics, of time consumed, technical difficulties as clogging of the filter, etc., the digestion efficiency, the cost, the hazard, and both techniques were working quite well. However, the KOH 10% was chosen as the best fit method. The next years, into 23 and 24, we worked on several species, monk seals, sea urchins, Mulus urmuletus, and Mytilus galloprovincialis. And in these cases, we don't only worked on microplastic ingestion, but we also wanted to see the effects of microplastic ingestion on these organisms. Finally, in 2025, we worked with the collaboration of the University of Athens on microplastic detection on Posidonia oceanica. In this case, we developed new methodologies on the detection of the seagrass leaves and on the detection of microplastics on seagrass rhizomes. In the first case, we used the stereoscopic observation, the scraping of the leaves and the epiphytes, and then the filtering of the material. And in the second case, the rhizomes were put in milky water, agitated in ultrasonic, and then again filtered the material. More information for these techniques can be found here. So to conclude, I would say that there are still many different methodologies on the detection on microplastics in biota and sediments. So intercalibration exercises are still very important. For example, the Quasimem initiative is in a very good direction, but it still needs to be improved and expand. We still lack reference material. We don't have clean water and sediment samples. We don't have variety of microplastic shapes and colors and sizes. And we still need harmonization of our protocols, although many steps, as I said, have been done. And of course, it's still important to do research on research of microplastics, to refine our methodologies, to improve our comparability of our results and accuracy of our results. And these are the references used for this presentation. And with this, I would like to thank you all for your attention. I would like to thank all the projects that funded this research all these years, and of course, the whole microplastic and marine litter team of the HCMR. Very much. And the next presentation will be from Julian. From GeoEcomar, but actually Theodora will do the presentation. Theodora, if you can hear us, can you share your screen at Zoom for the presentation?
Yes, I will. Hello.
Hello.
Can you hear me okay?
Yes, we can hear you very well.
Let me see if I can. Can you see the presentation?
Yeah, we can see your presentation. You can start. Thank you.
Okay, thank you very much. Hello, my name is Babush Theodora. I represent GeoEcomar in place of Julian Pojar, and I'm going to talk about methodological differences in microplastic sampling and analytical procedures based on what we do and how we do it in the institute. I'll skip over plastic definition, microplastic definition, since it was already covered before, and the presentation is quite long. And to begin with, GeoEcomar has been actively involved in microplastic research since about 2012 within EU and national supported projects. And then after a couple of years, in between 2020 and 2021, we finally got to have a microplastics laboratory in 2021. We started to do analysis on coastal areas, and the National Core Project for Plastic Litter started in 2023. For field work, we have boats that we use, Mare Nigrum and Istros. Then for sampling techniques, we use a Bodengreifer for sediment sampling and Neustonic net for water sampling. For coastal and shelf monitoring, it happens biannually on a Romanian coastline. What we do is 5 perimeters of water meters. We sample 3 locations: the swash zone, high tide, and vegetation line. And with the sediment sampling, we take from some inner shelf places too, and the surface water layer sampling with the net I was talking about. Here is the sediment sampling for inner shelf with the Boden. Now, analytical methods for we do sediment samples, water samples, and fauna samples. For sediment samples, we start with sieving. We don't have an electrostatic separator here at JV, but it was used on some samples in Germany by my colleague. After sieving, the digestion takes place. It takes about 5 to 7 days. It depends on the sample. And we use a combination of potassium hydroxide and hydrogen peroxide 1:1. After the 5 to 7 days digestion, we do a neutralization with formic acid. And then for sediment samples, we do a density separation with potassium fermiate. After all the chemical process, we do a filtration using those and a vacuum pump. And then visual identification and sorting on a digital microscope, and polymer identification using a spectrometer. Here is an example of how the electrostatic separation looks like that my colleague used in Germany. For water sample, the process is pretty much the same besides the sieving and separation. So we have the removing carbonates and organic matter with the digestion, neutralization, then the filtration. This is the vacuum pump, and the digital microscope for the visual identification. For fauna samples, again, the analytical process, it's quite the same, but before we do a morphological sample, for mussels, we measure them and weight them, and then we take out the soft tissue, again, measuring and weighting. And for mackerel, we take size measurements, and then we extract the digestive tract and the gills. Also, for every type of sample, we do a contamination control using blank blanks to try and minimize the contamination. For the analytical methods, here with the spectrometry, we have a Raman spectrometer from Craig Apollo that can identify a polymeric plastic compounds. Here are some results that it gives. Example of the results. Firstly, yes, we did found microplastic in all sediments, water, and almost all fauna samples. Higher concentrations were found near the Danube mouth and on urban areas. For sediments, we found a higher concentration in beach sediments. And for fauna, for fish, the digestive tract was more contaminated than the gills. Again, some sediment sample examples. Here we found that finer sediments usually contain a higher number of microplastics. Again, from those data, the Danube mouths are the most affected in terms of microplastic concentrations. Some more results in sediment samples. In the riverine sediments along the iron gates, the concentration was lower. Most of the particles that we identified were fibers. And then locally we found the flakes and fragments. As the type of the microplastic identified by the Raman and also here, but we don't have one here. 31% was polyethylene, 26% polypropylene, and 18% polystyrene. Usually, most of them, or most of what we tested was polyethylene. Some more recent samples that we took, 6 water sample from Sulina, Sfântu Gheorghe, Mamaia, Constanța, and Euphoria, and the mackerel and mussels. Here's the net again for the water sample. Some more results. Again, more recent results show that most of them were polyethylene. Here are some results for the mackerel, the digestive tract here, and fish gills. Some of them were taken in 2023 and some in 2024. Almost every part was contaminated. Again, with fibers mostly, and digestive tract samples from the mussels. Fibers were the most. By the color, we usually find black and then followed by blues as the most the biggest concentration of them. What we also could observe is that the size does not matter. It can be a small mussel and be as contaminated with microplastic as maybe a double size of one. Results from 2018 2018 versus 2023, we did observe maybe a small decrease in, but we also took some less samples. Concentration does decrease with distance from shore, and the Danube mouth and harbor cities are more contaminated than the Black Sea. Fibers are still the most encountered microplastics in both studies. For polymer identification, polypropylene, polyethylene are what we found the most. And some conclusion we came through is that as most each sample was identified with microplastic particles accumulation. Blank samples are for sure mandatory for each type of sample investigation for microplastics. Microplastic abundance depends on the sampling period of time, coastal beach segments, distance from the shore, type of currents, wind and wave regimes. Danube River and urban areas represents the primary source of microliter discharge in the Black Sea. Sampling methods and processing steps can determine microplastic recovery efficiency and the results, considering blank samples, significant contamination control. And the lack of standardized protocol for microplastic evaluation complicates the comparison of results a lot. Thank you for your attention. Also, if I'm not able to stick by the end for question and answers, I have here Julian's email, or maybe for more in-depth questions. Thank you very much.
Thank you very much, Theodora, for the presentation, and we'll make sure if there are questions to reach out at Julian's email. Thank you very much.
Thank you.
We will continue with the presentation of Win. Due to time difference, because he lives in California, he has recorded his presentation. So we'll watch his presentation now. And he's also said if there are any questions that you can email him directly.
Just a moment to solve a small technical issue here.
Okay, now we'll play the video from the presentation from Wien. So thank you for your patience.
Hey, Harm-Plast group, thank you very much for the invitation to talk with you all. Sorry that I couldn't make it there in person. I'm going to be talking about some of the new developments we've been making with Specy and specifically share some of the insights that I've had over the years on developing microplastic spectroscopy libraries. So when I started spectral analysis back in 2017, this was actually my first spectrum that I collected. This is a Raman spectrum of some fibers. You can see super high noise, really bad baseline, I mean, almost uninterpretable spectra. Come a long way since then. Also, the spectral libraries at that time, I was recommended to take this image and compare it to a reference manual and try to figure out what the unknown spectrum was. So we've also come a long way in that sense too. The classical spectral identification technique is to develop a spectral reference library, which is a set of known spectra, and compare it to your unknown. And we typically do this using a correlation coefficient search. So whichever spectra in the library have the highest correlation to the unknown spectra, we consider that the top match, and then you can look at several top matches from there. And visually, it looks like this. It looks like overlaying the unknown and known spectra and trying to assess, whether the peaks are corresponding between the two spectra. They have the same shape, the same width, everything like that. But really, where we want to go in the future is even a step beyond this. We want to get to a place where we can do automatic or almost automatic spectral analysis, where we can characterize the material type, the particle shape, size, color, for all the particles in our samples almost automatically. And this is going to really up our game. Sebastian Primka and others have been working on this for many years now. And our group has started working on this too and incorporating it into Specy. So I'm going to share some of the main learnings from that. Whenever you're developing a spectral analysis library, you really want to start by figuring out what your your classes are going to be. So you need to standardize the terminology that you're going to use for your spectral library. So for example, you don't want to have HDPE, LDPE, MDPE, all as separate classes if you can't actually differentiate them spectrally. And in the real world, usually those three classes are a good example of some that you should just merge into a single polyethylene category. And so here you can see an example of what we're currently working with for our harmonized classes. And you can see, for example, like quartz gets merged to a category called mineral. Tree bark might get merged to a category called organic matter. And you can imagine that there are many other possible terms that are going to get merged into those categories, like for mineral, maybe feldspar, or organic matter, maybe cottonwood. And then similarly for the plastics, our goal is really to try to differentiate the plastics as much as we can, but really some plastics can't be differentiated very easily. So you may end up kind of lumping several different categories together. So for example, here we have polyacrylamide and polyamides, polyesters, terephtalates, for example, are getting merged into the same category. So these are some trade-offs that you can either, or some ways to lump the data that you can either derive through trial and error, or you can use like a PCA or you can use fundamental theory of spectroscopy to be able to derive these harmonized categories. And we have been working on a new technique to be able to assess microplastics using plate readers. So we think this is really gonna up our throughput for microplastic analysis. Sebastian Primka is the one who taught me about this. He had one of these plate readers, and I visited him on Haviland and helped to develop the first iteration of this method. We were able to collect 6,000 spectra from a variety of different materials very quickly, just in a couple months. And this is, typically a microplastic study, maybe only 600 spectra coming out of there. So 6,000 spectra is really an order of magnitude increase in what we were able to do. And some of the things that we learned while we were developing this method is that there's a lot of spectra out there in different material types that are really difficult to identify or to collect a good sample of. So for example, tire wear particles and thick particles a lot of times have total absorbance. So you can see here in this, on the right-hand side here, so we have tire wear, tire rubber, and then we have the two different plate readers, and you can see just very strong baseline signals, not a lot of differentiation in the peaks. ATR was able to collect a decent signal, but there's real limitations to the spectral collection mode that you choose and how you end up doing the sample preps. That'll end up determining the quality of the spectra and how well you're able to identify it ultimately. Also, with the really thick particles, so we had these thick plastic pellets, and those will end up getting these total absorbance saturation here at the top, where you have these like big plateaus. There's still quite a bit of spectral information, on the sides, but it's quite distorted. And a typical correlation-based search would have a hard time differentiating this from another thing that has the same, artifact here of the total absorbance piece. And we ended up testing this in OpenSpecy to try to assess, how well we were able to identify these reflectance and transmission plate reader spectra using the standard OpenSpecy library at that time. Back in that was, let's see here, when was that? It was back in like 2023. And at that time, the OpenSpecy library just had ATR spectra. And so ATR spectra was able to be identified pretty decently, over 50% with out-of-the-box accuracy, which is kind of the worst case scenario. And then, a factor of 2 less for reflectance and transmission plate reader spectra. So really, when you're developing a spectral reference library, you want to be developing the library so that it will produce similar spectra to what you're going to be collecting. So if you're going to be using a plate reader, then you need to have a plate reader library so that you can have high confidence IDs. If you're going to use ATR, you need an ATR library to be able to really have the highest confidence IDs. Some of the other known challenges, this is what y'all are all about here. Weathering, more about this than I do. These weathering fingerprints are well known. You have the hydroxyl peaks and the carbonyl peaks. And both of these are definitely something that if you can add weathered spectra to your spectral library, you will end up improving your match quality, your match accuracy. The study that's cited here definitely can attest to that. But also Chibuka is another study that looked into this and really showed that all you need to do is add more weathered plastic spectrum. Some of the things that we're not quite sure how to deal with yet. One of them is mineral doped plastic. So if you have like a fiberglass, for example, fiberglass is a combination of glass and plastic resin. That glass signal, that SIO peak here, is going to be really strong. And in a correlation-based search, you'll have a hard time differentiating this from just a mineral signal. The peaks that are related to the plastic are a lot smaller and very weak in comparison. And so in this case, honestly, we haven't quite solved this yet. A lot of we don't have a good way to accurately ID these using spectroscopy. Similarly, the plant cuticles have been found to be a interfering identification to polyacrylamide. Polyacrylamide signals are quite similar to plant cuticle signals. You could go in and manually kind of curate this, and I think a very highly trained spectroscopist probably could accurately differentiate these spectra, but using the more automated approaches, it's just going to be very hard. Sebastian Premke's group did show that if you add in plant cuticle spectra to your library, you will be able to improve the differentiation between the natural and the synthetic materials here. And in OpenSpecy, we're really trying to push on this vision right now to be able to automatically characterize microplastics by material, shape, count, color, and size. And I'll share some of the key learnings from that in terms of library and analysis development. So what we did is we took homogeneous plastic and mineral particles and put them across a stainless steel mesh and then we scanned the surface using our Thermo Fisher IN10, did this for 20 different materials, and really we were doing this so that we could test our automated algorithm. We didn't add any of these spectra into our library. We wanted to create a benchmark data set that you can test against. And this is something we're working on publishing right now, so I'm happy to share it. And with our automated algorithm, the simple steps are you start with a visual image, and then you collect a hyperspectral image. We can figure out where the particles are in that hyperspectral image using the signal multiplied by the noise. And then we take that and threshold that heat map so that we can pop out where the particles are. So you have like a binary image of just black is where the particles are, white is no particles. And then we can collapse every single pixel for each particle to a single spectrum that we can then identify. And this really speeds up your computation time quite a bit. And then you can get maps that look like this, where you can see, oh, okay, that's particle 131. And then we can do a visual overlay to QA/QC. So this is where we're working on heading right now. And we're already using this here at the Moore Institute. We are an accredited lab, and this technique has gone through the eLab accreditation process. So really excited about that too. This is one thing I really want to hammer home is that I think that right now in microplastic research, we have not been characterizing our uncertainty enough. A lot of times we just characterize, what's our proportion of correct identifications. That's one piece of the puzzle. But also, what about the count of microplastics in the sample? What about the size of the microplastics? So if you're going to develop an automated analysis technique, we should be characterizing our accuracy for all these different things because you'll have different accuracies for each one. So for example, we're overestimating count by about 20% with our automated technique, underestimating our identification or incorrectly identifying things about 10% of the time. And our sizes are about 10% too small. We also characterize the relative standard deviation, which characterizes the uncertainty around those values, which is really important because that metric, I mean, it's great if you have 100% accuracy, but if you have 50% or more relative standard deviation around that, then actually any individual point is going to have a lot of uncertainty around it. So you have to collect a lot of data points to be able to get that 100% accuracy. Also, we're always trying to push on the analysis time. I mentioned some of the things that we're doing to speed up, but right now we're at about a 1 minute analysis time for 100,000 spectra in a map. And I think we're really where we want to be, but I think that we need to proceed cautiously because this is not perfection. This is not like a silver bullet. We still have work to do to make this get to the stage where it's going to be something that people can consistently rely on and not have to really go into the back end of it all the time. I'm still constantly refining this tool. And the main thing to get down is really those relative standard deviations. I want to get those very low, like less than 20%. All right, some of the other things. So when you have some of the other known issues that I just wanted to highlight for these automated analysis techniques, when you have touching particles, they end up getting merged into one. You also can get really poor signal near the edges of the particles. This might be a good signal to add to your spectral library if you think that this is going to be a common thing. You can get ruptured particles at these poor signal regions. They can end up basically like one region was out of focus, one region was in focus, and so you end up getting these gaps. And particles can move around in between the time when you're collecting a visual image and a hyperspectral image. So really, I think this is kind of an instrument issue. Is there's too much vibration going on the stages. So in this one, we have like bad allocation between the visual image and the hyperspectral output that we've gotten in. And also, you really need to make sure that you have a good background. It should be very flat. Should be all the same height. In this image here, we did not have a flat surface. We had a really rough surface. We had this stainless steel mesh that had really wide holes. And you can see all these different little false particles that are being ID'd here. This is just the stainless steel mesh holes. So if you don't have a flat surface or flat enough, we have shown that you can use stainless steel mesh if it's tight enough. But if it's too wide, you're going to end up getting something like this. Also, if it's not perfectly flat, you'll end up getting these gaps where basically this should have been, based on what we're seeing up here, this should have been also identified as little holes where particles would be, but it wasn't because it was out of focus. So in conclusion, we really need more spectral libraries. We need more diverse libraries. We need to continue to push and understand our uncertainties and the biases of these techniques. We have we're working on a graphical user interface that opens Specy and speed improvements to be able to work with even larger maps. Right now, we can do like 100,000 spectral maps pretty easily, but a lot of the maps out there are millions or tens of millions even that people are developing today. And some of the big questions that I have are, are there some new techniques that we could use, like time resolved Raman or time resolved IR, potentially adding in, complementary techniques into the analysis that are also high throughput to be able to give us more certainty, understand that, the mineral doped plastic or something like that a little bit better, get some higher quality signatures. So thank you very much for your time.
So this was the presentation of Win. And as I said at the beginning, if you have any questions for him, you can email them directly to him. Now we'll have a 10 minutes break. And then we will return at 12 o'clock and we'll start with the presentation of Dr. Evdokia Sioannidou. So just a quick break and we'll be back at 12. Thank you very much. So hello again. In any minute, we'll connect with Dr. ΕΛ.ΚΕ.Θ.Ε to proceed with the presentations. Evie, if you are at the Zoom, can you please, all right, yeah, we can see you. Can you please share your screen for the presentation? Evie, can you share your screen for the presentation, please? Evie, can you ask at the Zoom to be unmute?
Yes, now I think we can
perfect. Super, super. We sorted it out. Yeah, if you can share your screen, otherwise I have your presentation also here.
Yes, I think that I cannot share my screen. I don't know why.
All right, then we'll share it directly from here. You will just have to tell me next so I can proceed, go to the next slide. Would that work fine for you?
Yeah.
Okay. Okay. You can start and let me know whenever you want to go to the next slide.
Okay, hello everybody. I'm Εύη. I'm a Marie Curie postdoc fellow at Cyprus University of Technology, and I will present you the work that has been performed in both Technical University of Crete and Cyprus University of Technology the last years. And I will concentrate on the fate of plastics in the marine and terrestrial environment with a focus on biodegradation. Next. As you know, the global plastic production is increasing, and however, you already know that. I want to present here that the fate of bioplastics also, because bioplastics production is also increasing, and nowadays is more than 2 million tons, but it will exceed 6 million tons in 2030. So I think that we should include bioplastics also in the agenda of plastics. Next. So briefly, the fragmentation of plastics when they enter the marine environment, they undergo weathering, they subjected to photooxidation, and together with mechanical abrasion, and then you can see that hydroxyl and carbonyl groups are developed on the surface, and the polymer loses its ductility and becomes brittle, and then a lot of cracks and flakes are formed on the surface, and this leads to the generation of micro and nanoplastics. Next, I think, a lot of next. So this was an aging experiment that was performed in simulated coastal and pelagic conditions. With these experiments, we investigated the correlation of chemical properties and the generation of microplastics when the films were exposed to UV radiation. Next. And you can see the correlation of all the parameters that was studied, and you can see that there were negative and positive correlation. You can see that the photodegradation is a dynamic process, and the induced surface changes provide more available sites for reactions, and then this favors the cracks and the holes on the surface of the polymers. The thing that was interesting, according to our mind, was that there was a correlation between the carbon index and the molecular weight of the polyolefin films. And in fact, this correlation was negative. So as the carbonyl index increased, the molecular weight decreased. And the other thing that we noticed is that the carbonyl index followed a pattern. So in the beginning, the CI values exhibited a first state which corresponded to a low weathering phase, and then a rapid growth phase, and then a stationary phase, which we suggest that this means the generation of microplastics. Next. And so the thing is that when we take the FTIR spectra of heavily aged films and we try to see their similarity with the commercially available libraries, it was not, the similarity was very, very low. And when we check the similarity of the generated microplastics with micro FTIR, then the libraries could not even identify that these were microplastics. Next. And then we proceed with some mesocosm experiments where we use 40-liter tanks. And in these experiments, we investigated the combined effect of biotic and biotic factors in the weathering process of microplastics. Again, we used polyolefins. This time we used virgin pellets and weathered pellets, and to see if there is a difference in their fate. You can see here the carbon index of both virgin and weathered pellets. In fact, they follow an opposite trend. For example, the carbonyl index of virgin pellets increased and then decreased and then decreased again. But for the weathered pellets, the carbonyl index decreased after exposure and then increased again. So we hypothesize that there are consecutive cycles involving microbial removal of the weathered layer, exposure of the first virgin layer, and then the re-deterioration of this fresh fraction, and these cycles are repeated. And again, the heavily weathered pellets showed very, very low similarity with the commercially available libraries. And these experiments suggest that it's very important when you collect a sample from which phase the particle is when you collect it. Next. And now about the bioplastics, because these are very new plastics, and we don't know, they are called biodegradable, but we don't really know if they are in the natural environment. So we performed experiment in collaboration with the University of Torino, and we exposed again the pellets of PLA and TPS in simulated coastal and marine environment. And you can see at the left part of the slide the pellets along the experimental exposure, and you can see that the size could not really decrease significantly, and we can see only color changes and some biofilm adhesion on the pellets. Next. And this is the microscale effects. You can see the virgin PLA pellets and the pellets after the exposure. You can see the deep cracks and holes on the surfaces, and some particles that are generated and ready to detach from the parent polymer due to exposure. And you can see also the FTIR profiles of the pellets, and they are very, very different compared to the parent polymer. And this is the problem also with the bioplastics, because the libraries don't have many spectra, so it's even more harder to identify these weathered bioplastic pellets when you collect them from the environment. Next. And then we also noticed that these bioplastics generate microplastics that we could count besides the same pictures. In fact, they produce more microplastics after longer exposure to the environment. And we also noticed that they produce nanoplastics, and the size of these nanoplastics were more or less 250 nanometers. And the microplastics that were produced were mainly in the shape of fibers. Next. And then we go to the terrestrial environment. You know that plastics are extensively used in agriculture for many, many reasons, like greenhouses, mulch films, boxes everywhere. So we again performed experiments using soils from tomato fields and fields with olive oils. Next. This is the experimental design. We used both plastics and bioplastics with 0.1% concentration, and we added the pellets in several depths in order to see if there is a depth effect on the degradation. Next. And here you can see the FTIR profiles. These are the films of HDPE and PLA. In case of HDPE, you can see that the parts of the films that were in depth more than 5 centimeters, these films were very similar with the virgin films that we introduced to the soil, while the part of the films that was exposed to the environmental conditions and microbial activity, these films were very, very different from the initial film, while the PLA films, all the parts were quite different from the FTIR profiles of the virgin PLA films. Next. And here I will show you some results, because we try to develop biorecycling methods of bioplastics. The thing next. So I will just say that we measured in control conditions the effect of microbial activity, and by microbial we mean communities comprised of microbes, fungi, and chlorella. And again, we noticed that the FTIR profiles of pellets that were subjected to microbial activity were very, very different compared to the initial parent polymers. And this time, the regions between 1000 and 1020, these regions were, the differences were located in this region. Next. So to conclude, after all these experiments, we can suggest that the carbon index can be used as an indicator of microplastic generation. Bioplastics produce microplastics and nanoplastics when they are exposed in the marine environment. The conventional and bioplastics cannot be degraded in the soil environment in less than 200 days. And when we take the virgin microplastics and we subject them under weathering, or we expose them to microorganisms in natural or in controlled environment, Then their FTAR profiles display significant alterations compared to the parent polymer, and the longer exposure leads to lower similarity with the commercial libraries. Next. Thank you very much.
Thank you very much, Evie, for the presentation. And if you can stay with us until the Q&As will be great. And now, Mariana from VLIS will present. This one,
Okay, thank you very much. So my name is Mariana. I'm from the Flanders Marine Institute in Belgium. And today I'm actually presenting a work that I did before joining BLIS at the University of Porto during my PhD. And as you know, the plastics, when they enter the environment, they are exposed to several different environmental agents, such as radiation, variations of temperature, but also some chemical agents that can lead to modifications, both chemical and physical. And these then aged particles can, because of this, interact differently with other contaminants that exist in the environment, such as, for example, pesticides. So one of the main hypotheses that I was testing during my PhD is that if due to this degradation, the microplastics can be transport vectors for micropollutants. And micropollutants are contaminants that exist at very low concentrations in the environment, usually nanograms or micrograms per liter. And I was looking mostly into pesticides and pharmaceutical substance. And you might ask, but is this relevant? And I will give one example, that is when microplastics go through a wastewater treatment plant. And in this case, in the effluent, you have both microplastics, but also these contaminants. And it has been proved that for both of them, some of these particles and some of these contaminants pass through these treatments without being degraded. And so they are released into the environment also together. And so they can be transported, and they can be released to rivers, and also then, of course, because everything is connected, also be released into the ocean. We have the potential of these particles reaching organisms, where they can then release these contaminants into the tissues of the organism and lead to potentially toxicity. And because the group that I was in was not on marine research, I did these experiments actually on plants. So I was testing phytotoxicity. So during my PhD, I looked into the degradation, I call here aging. I also looked into the sorption on the surface of the particle, so adsorption. And I also looked into this release of the contaminants. During this presentation, I will mostly focus on the aging component because I was asked to present on weathering and also didn't have enough time to present everything. So the types of the degradation that I performed were with virgin microplastics. So it was commercially acquired microplastics of 3 polymers, low density polyethylene because it's the most produced polymer, polyethylene, and also one of the most found in the environment. I also select PET because in opposite, it's one of the least studied in this type of studies. And I also selected PVC, the rigid version of PVC and plus size PVC because it was also had very low studies published at the time, and it's a very relevant polymer. So I did 3 different types of degradation. I did chemical exposure with ozone. We used 2 different settings, ozone dissolved in water. And this is used, for example, for the disinfection step in a wastewater treatment plant. I also did a degradation with ozone gas, so direct exposure to ozone gas. And this is also used in disinfection, for example, in the food industry. And these were done for 1 hour, which is longer than it's usually done, but it was also so we could measure some modifications. We also did radiation exposure with UVC, which is the strongest UV radiation, doesn't reach the surface of the Earth, but is used also a disinfection technology, for example, also for the wastewater. And finally, I also did a simulated solar radiation treatment, and this was to directly compare the results also to the natural weathering that was performed. I will explain in the following slide. For the radiation treatments and also, the radiation treatments, so this was done for 120 hours or 96 hours, but I was measuring and collecting samples throughout this time. So I was actually measuring different characteristics of these polymers throughout time. So finally, we reached the weathering, and this was done in the rooftop of our department at the University of Porto. And we exposed the different types of microplastics in two different types. In one of the trays, they were just exposed to the variations of the temperature, to the natural solar radiation. And in the other one, apart from that, we are also collecting rainwater and adding it to the quartz Petri dishes. So this was done during 13 weeks. The idea was to do it in the peak of the year where you have more hours of light per day. Starting before and ending after the solstice. And we were collecting samples every week. And during this time, we were also using the National Institute for Meteorological Data and Atmosphere to have data on the meteorological conditions and also on the levels of precipitation. And based on the precipitation patterns, we were collecting directly with the system during the design that you see on the left, rainwater that was added manually to the Petri dishes. So I will only present some results for polyethylene. And here you see the first characterizations that we performed with the ATR FTIR to have an idea on the chemical structure modifications. Here you see the spectra, they are overlapped and they correspond to the very last sample that was collected, so for maximum time of exposure. And you can see compared to the version spectrum, there was the increased absorption peaks throughout the spectra. And this mainly results due to the oxidation of the surface of the particle. And as we know, one of the most famous peaks is the carbonyl peak. And we use this to calculate the carbonyl index that in this case was done with the height of the peak and normalized with the methylene group. And based on this, and because we were collecting this spectra throughout the degradation, we were able to plot the carbonyl index through time for both the simulated treatments and also for the weathering in the rooftop. And you see that even with 1 hour of exposure, the ozone gas was quite strong in increasing the carbonyl peaks. You see the point in red in the first plot. And also in blue, a bit below, with dissolved with ozone. And of course, you were expecting that the one with direct gas would be more strong. Also very interesting that we got higher carbonyl peaks with the simulated solar radiation compared to the UVC, which is a quite strong radiation. And then for the rooftop weathering experiment, we were able to see that for most time, the results were very similar because there was also not a lot of rain. But then at some point, the samples that were added rainwater started to have a higher carbonyl index that then decreased. And actually at the end, it was the same. Were these samples equally degraded or they were actually in a different stage? And this was also something that we were interested to see. And also you can see that at the bottom left, we also plotted the simulated radiation results that were just converted into weeks based on the time of light that we had in those first 2 weeks of the experiment. So then, as I mentioned, we were interested to see if then the carbonyl index would be enough to evaluate the degradation. And so we also looked into the surface morphology, which is a quite different parameter. And we were able to see for most of the samples, there was not possible to identify any modification. However, we saw that for the rooftop weathering treatments for both without and with rainwater. But the samples with rainwater actually showed more deeper cracks. And not only that, but there was also the colonization of these particles with microorganisms. And you see around the colony also some bigger fractures. So this also in line with what was presented in the previous presentation is that the carbonyl index probably decrease because we were having these fresh areas of the surface of the particle actually being uncovered and the degraded material being released. And finally, we looked into the degree of crystallinity. So this gives us information on the percentage of the polymer that is amorphous versus the crystalline component. And for most samples, there was not significant changes. However, we saw that after exposure to either simulated solar radiation, but also due to weathering, there was an increase of this crystallinity. And this was important information to have because then, as I mentioned, we looked into the capacity of these microplastics to carry other contaminants. And all these modifications are important to understand how these components, these chemicals can link to these particles. And so here I have the results that were done for the ozone gas degraded particles and also for the two after weathering. And you see that there was, compared to the version microplastics, an increase in the global sorption capacity that was quite significant after this degradation. After ozone, there was already several chemicals that were not before sorbed that started to being sorbed, but after weathering, this increased a lot. And indeed, for one of the, so these chemicals were 6 pharmaceuticals and 4 pesticides. And one of the pesticides, which is pentachlorophenol, actually we could not detect it after the weathering treatment in the liquid phase. It means that most of it was then sorbed into the microplastics. So, and why does this matter? So then, because indeed they could potentially be transport vectors for these contaminants, but there's another question is that if then they can release and lead to toxicity. And so we performed these phytotoxicity tests with 2 species of plants, Lepidium sativum and Synapsis alba. And so these were experiments that were done with 10 replicates. We did negative controls, positive controls with the chemicals, but not the microplastics. And then we did tests with the microplastics, but without the contaminants sorbed in them, version and degraded, and also then the same after sorption. And we saw that for one of the species, there were no effects that were observed, while for the other species, there could potentially be low effects on the early growth of the roots. And this was observed for the microplastics that were weathered and had contaminants sorbed in them. So this was a bit of insight into the research I did during my PhD. As I mentioned, currently I'm working at BLIS and doing a bit different work, more related to the INSPIRE project. And also I've been participating with the Harm-Plast project, which I'm very grateful for because it's another opportunity to continue to work a bit on the weathering and also how we can improve the harmonization and also for the evaluation of these important aspects. So thank you very much also for allowing me to join this project, and thank you for the invitation to present today. Thank you.
Thank you very much, Mariana. And last but not least, then I will present.
Hi, everybody. My name is Dana Ipatziou. I'm a biologist at the Hellenic Center for Marine Research at the Institute of Oceanography. Okay. Today, I'm going to talk to you about a study that we have been doing the last year about copper adsorption and desorption from weathered microplastics during in vitro digestion. So I don't know, probably you all are familiar with the Trojan horse effect. The microplastics are carrying chemicals. The chemicals can be either inside the polymer matrix, like the plasticizers, for example, or they can be adsorbed on the surface of the microplastics once the microplastics are released in the environment. And for example, they can be like environmental contaminants that already exist in the environment. So the microplastics, upon ingestion by an organism, will enter the gastrointestinal tract of the organism, where is actually an environment with high acidity and enzymatic activity that can promote the leaching of these chemicals. And then the chemicals can be potentially accessible, like bioaccessible to the organism. So copper is a heavy metal, is an environmental contaminant. It's been widely used in manufacturing and daily life, and it has a reported massive discharge in the environment. It is a toxic compound and it cannot biodegrade. Studies have been done on the absorption of copper on microplastics, and we have seen that the polymer type, that actually the absorption of copper depends on the polymer type and on the particle size, among others. So aging as well influences absorption of chemicals on microplastics. We can see that the aging actually increases the fragmentation of the surface of the plastic. That can increase the surface area of the plastic and then the absorption capacity. You can see in the figure, these are a polypropylene pellets, and you can see in the right one, in the B, a rough surface and severe cracks after the polypropylene was exposed to a xenon lamp. The authors also chemically analyzed the pellets, and they found increased the percentage of oxygen content and also increased hydroxyl, carbonyl, and vinyl group formations. So the aims of the present study are to assess absorption and toxicity of copper on pristine and weathered polypropylene microplastics, and also to investigate the dissolution and toxicity of associated copper after a simulation of microplastic digestion by the rainbow trout, a freshwater fish. So in the schematic below, you can see the experimental design. First, there was a series of experiments to actually absorb copper on the microplastics, on the surface of microplastics. And then a static in vitro digestion took place. Actually, what happened? We put microplastics into this reaction vessel, and then there were two phases of digestion. The first one was the gastric, where the digestion fluid contained the enzyme pepsin, and the pH was set to 2. And then there was a different reaction vessel with a different digestion fluid that contained bile extract, pancreatine, and the pH was set to 8. The duration of the gastric phase was 3 hours, and the duration of the intestinal phase was 23 hours. During the digestion, we collected samples of the liquid phase in several time points to assess the dissolution of copper from the microplastics. And at the end, we took the liquid product of the digestion to see whether actually this is toxic. So we assessed the toxicity in bacteria in 2 model species, and we wanted to study how the microbiome will actually be affected after the exposure to the digestion fluid. And also our plan is to test the toxicity on rainbow trout cell lines. So we used 2 kinds of microplastics, the pristine microplastics and weathered microplastics. The weathered microplastics were actually naturally weathered, were derived from a rope that we found beached during a beach cleanup. Both microplastics were identified as polypropylene, and the median size of the pristine ones were at 52 micrometers, and the weathered ones were at 21 micrometers. Additionally, the aspect ratio of the microplastics, the pristine ones was lower than the weathered ones, indicating that the pristine were more rounded, while the weathered microplastics were more elongated. So here you can see the results of the copper absorption experiment. We see that copper was absorbed mostly on the weathered microplastics, but also copper was absorbed on the pristine microplastics. The pristine microplastics didn't leach any copper, while the weathered microplastics, they leached small amounts of copper. And we did a set of experiments to assess the toxicity of only the microplastics in bacteria. And we found actually that Bacillus thuringiensis was sensitive to the weathered microplastics by themselves without any copper associated. Only, of course, in the highest concentration, that is 200 milligrams per liter, it's a quite high concentration. And then Pseudomonas aeruginosa was sensitive to all conditions. So here is the first slide of the digestion experiment. So what you can see is the dissolution of copper in the gastric phase. And we did two sets of experiments. So the first one did not contain food particles. So it was only the microplastics in the digestion fluid. The second one to the right, it contained food. That is the environmentally relevant scenario, because almost never an animal can consume microplastics by themselves alone. Usually there is food as well. So we can see in the left, where there is no food added in the reaction, we can see that copper is dissolving, is actually desorbed from the weathered microplastics with associated copper, and this is increasing with digestion time. On the contrary, in the right graph, we can see that when the food is present, there is less copper actually leached from the microplastics. And if you see the copper control, that is the blue dots on the top, that is only copper, we can see that at 3 hours of digestion, the copper that is available is actually lower, and that can indicate that it absorbs on the food pellets. So moving on to the intestinal phase, again, it's the same setup. At the left is the no food experiment, and in the right, there is the experiment when the food is included. And we can see that in the no food experiment, there is no copper available during the whole digestion time of the intestinal phase, that is 23 hours. And in the right, where the food is present, we see that there is desorbed copper as from the weathered microplastics, the yellow dots, with a peak at the 21 time point, and then it is reducing. So if we have a closer look at the 21-hour time point, we can see that the weathered microplastics are dissolved, there is copper dissolved from the weathered microplastics, significantly more than the control, but also we can see that even the pristine microplastics are leaching copper, and the pristine microplastics with associated copper, and the weathered microplastics by themselves, but not significantly different. So now if we move on, we focus only in the weathered microplastics with associated copper, and we can see in this graph, actually, I don't know if you can see it better there, in this screen is not really easy to see. So there is, this graph has collected both gastric and intestinal phase. At the left, there is a background of green that is indicating the gastric phase, and the orange pink is indicating the intestinal phase. And we can see with the purple dots, the experiment with the food, and the yellow dots, the experiment without the food. And we can see that actually the presence of the food during the gastric phase is reducing the copper dissolution, while during the intestinal phase, the presence of food is increasing the copper dissolution. And actually this is really important, because during the intestinal phase is where actually the nutrients are being absorbed by the organism. So any chemicals that are absorbed on the food or on microplastics, in our case, will be available to the organism during the intestinal phase. They can actually go through the intestinal lining and into the bloodstream. These are the experiments where we took the liquid product of the digestion, the end product of the digestion, and we tested again these two bacteria, the Bacillus thuringiensis and the Pseudomonas aeruginosa. We didn't find an inhibition effect in the bacteria when they were exposed to the liquid digestion product. These bacteria are not are model bacteria. They are not native to the gut microbiome. However, this information is actually giving insight on how the gut microbiome bacteria can react when they are exposed to this digestion product. So the outcomes of this study so far, what we have found out is that the weathered polypropylene microplastics show toxicity, they show growth inhibition for Bacillus thuringiensis and Pseudomonas aeruginosa. The weathered polypropylene microplastics have higher absorption capacity than the pristine ones. We see that the gastrointestinal tract is a dynamic environment. The acidic environment and the enzymatic activity are promoting the dissolution of microplastic-associated copper. And what we saw is that the presence of the food is changing the equilibrium, increasing the copper dissolution during the intestinal phase, and that can increase the bioaccessibility of adsorbed copper. Also, the bioaccessible fraction did not affect the bacterial growth. So for the future, we plan to assess cellular toxicity of this bioaccessible fraction using a rainbow trout cell line. So for this study, I want to thank Madoko Tsiri from the Marine Biology, Biotechnology and Aquaculture Institute of HCMR, that is my collaborator for this project, and Tonia Despotidi, that analyzed tons of samples for atomic absorption spectroscopy, and also the Marine Litter Research Group of HCMR. Thank you very much for your attention.
Thank you very much, Danai, for your presentation. Well, now if there are questions from the audience here or from the people online that they have shared some questions via the chat, it's the time to shoot. I hear. Okay.
Can you share the methods used for the processing of the feeds?
Θέλω να το διαβάσετε πιο δυνατά.
We have
Maria, you can email me if you want, but since we are still busy with the data and these were just preliminary, would rather share the methods in like a couple of months when will we be published. But you can always email and discuss some few things if you want. There are no more questions at the chat, right? No. Are there any questions from the audience here? Ναι.
Thank you, Argyro. Thank you all. They were very interesting presentations, although I missed some of them due to other commitments. It's very important to emphasize the need of harmonization within and across countries, especially like countries like Mediterranean, in all those different aspects of floating or other microplastics. But my question was from, let's say, from a managerial point of view. I do understand the merits of the science, and I do support the need to have all the scientific work. But for example, in your presentation, you said that there was a discrepancy of 10% or something like that, if I remember correct, among the different instruments, or difference. Yeah, it's not important, but I mean
for the library differences, right?
Yeah, but how important is that for a managerial point of view, and from for a politician or decision maker? And the second question is, you started with this kind of difference, I think it was 13% or something, but then you applied some corrective factors, if I'm not wrong. And how much did you manage to reduce this difference after your work? Okay, thank you.
Thank you very much for the question. For the first question, for the first part of the question, we observed indeed differences reaching from 6 to 15% between the libraries of the instruments. And how we can actually sort this out is because all the instruments that they are using at SNR and at VLIS, they correspond to libraries that use pristine material. So they're called the commercial libraries. So then when you try to match a spectra from a weathered plastic item that you collect using a mantonet in our case, then the spectra will have a lower heat quality index with the library spectra. So to sort out these, there are two options. First one, you use weather libraries. That's what our aim is, that in the end, our spectra, the spectra from all 3 laboratories will be uploaded to the open Specy. And then end users, like all of the labs, instead of each one of us using her own libraries of their own instrument, and many times people also add their own home libraries that they make, then we can all compare our spectra with the libraries from Open Specy, so which is a much greater library database. And also the advantage of us having tested the very same item with 3 instruments is that we will be sure indeed, like Mariana will give the final answer if our item, for example, that we had differences, what it will be with the 3rd instrument. Because so far at Open Specy, many users, they have been uploading weather spectra to contribute to the community, which is great, but there were a lot of errors. So we were discussing with Win, because we're trying to match a library spectra, and then it would say, for example, polyethylene, but we had something else, which was wrong due to the weathering. So this is more the methodological approach for the first question. For more legislation or something, probably Giuseppe could give more insights on that. I don't know about if you want, yeah, or you can come here, Giuseppe. And for the second, it was for the carbonyl index with the pre-processing, indeed, because actually the carbonyl index so far is mainly used for experimental data, like the data that Mariana presented and Nevi presented. And in those cases, there are several carbonyl indexes used, but in our case, we use data collected and items weathered in the environment. So we don't know, like Mariana presented, like the steps or if they knew exactly the weathering process. For us, we have the microplastics and we have no idea for how long they have been weathered. So then when we had the carbonyl index, in order to estimate the weathering status, we observed that the raw data were totally different between the instruments. The interesting thing here is that well, the carbonyl index we use, the author that actually created and suggested this index, suggested not to use pre-processing methods because it could potentially alter the index. But the author that suggested that was doing experimental work. But in our case, if we use the raw data, we cannot actually really compare, or because we are going to use the carbonyl index as a metadata at Open Specy, then we will have, let's say, one item would have 3 spectra and 3 different indexes, which is wrong because it's the very same item, so it should have the very same weathering status. So with the pre-processing methods, we can have in the end one carbonyl index value, so we are more sure of the weathering status of the microplastic. But of course, as also Evie and Mariana presented, it's a huge discussion about the carbonyl index. And so far, there are 3 more publications that have used carbonyl index on environmental spectra. The rest are mainly for laboratory data. So it's new, we're trying our best, and we hope that we can have some nice results. So far, we do have some nice results, and we hope also with the 3rd instrument to be even more accurate about the data. And yeah, for the first part, Giuseppe, if you want for the legislation to say a few things. If you want to come here or there.
Yeah, no, I just wanted to briefly add that I think the policy and legislation has not arrived to this point yet, to this level of detail. Most of the policy has been basically developed looking at macro litter, what are the most common items, and consumer items. So the policy now is addressing consumer items, not microplastics. For microplastics, The marine strategy developed, I think they are in the process of developing threshold values, baseline values, on which will be used to monitor trends in the future. But this level of detail, I don't think it goes down to the polymers. It goes into detail for items, for instance, glasses or bottles or plastic or shopping bags or these kind of things. But yeah, polymers is a bit, research in this case is well ahead than policy, of course. Just wanted to add this.
Thank you very much, Giuseppe.
Hi, excellent presentations. I have no knowledge whatsoever about polymers, and just from an analytical standpoint, I found your comparison between the intercalibration between the labs and after applying the baseline correction, it was very, very interesting and obviously gave great results. So why don't you use this type of approach in the open spec database by having the raw spectra and also a processed spectrum? So people can have access to both the spectra and can choose for themselves which one is gives the better results. And you said there are 3 more publications that came out about the environmentals. What type of spectra were they using? Pre-processed or raw data?
Thank you very much for the question. For the publications, yeah, there are 3, and all 3 of them are from Japan, actually. And the 2 of them, they have used the raw spectra. And the one was actually used one pre-processing method, one baseline correction, and compared different carbonyl indexes. And actually, this publication said that it had the best results using the SAUB carbonyl index. And that's why we also used that, because it was the only one with environmental data. And then for OpenSpeki, indeed, so far what WIN has, you have the option to upload the spectra as a raw spectra, or you have the option to the spectra to be already, he also follows a kind of baseline correction and mean-man normalization. So you can also match your spectra with the corrected spectra. So indeed, he has chosen to do this. And in my perspective, when we have weathered spectra, it's necessary to have some correction, even if you want to do polymer type identification, or if you want to use it for the carbonyl index estimation, for sure. So the correction that the WIN is using for the baseline correction is more similar to the second baseline correction that we presented today. But yeah, this is what he is doing. And we hope that it really, the libraries, the pool of libraries in the OpenSpeki really grows. So then it will be very helpful for all of us. Because for me, it was striking to see that we even had, like, I have in mind that for polyethylene and polypropylene, I'm pretty sure, I'm pretty confident for the spectrum. And then when we had already the differences, okay, it was the percentage was small, but I was, okay, it was very interesting that even for polyethylene and polypropylene, we had some library differences. But again, the differences were observed for low heat quality index spectra, which was between 60 and 80%. So this is also another topic, because some publications, they say, okay, we have used spectra with heat quality index above 60%, or others above 80%. So yeah, 60% is a more not so strict threshold, but then you can have some mismatches, whereas 80% is more strict, so you can have some false negative, like you keep out some plastics, but at least you're more sure of what you have identified. Because for the spectra that they were above 80%, we had 100% matching between the 2 laboratories. So this is also critical. And again, comes back to the weathering process.
Can you hear us now? Okay, thank you. So I will repeat my question. It is addressed to Evi Siranidou and is related to the use of bioplastics in agriculture. Because we know that this is a sector where the use of plastic films contributes very highly to the production of generation of microplastics. And my question is related to the biodegradability of these bioplastics or biodegradable plastics, because I understand there are two different definitions here. And whether you can explain us a little bit better and your opinion in their ability to produce microplastics and whether they are a better option to the conventional plastics. Thank you.
Hello, I have problems with mute and mute. Okay, thank you very much for your question. Bioplastics, the definition of bioplastics is controversial. More or less, they are divided to bio-based, bio-based and biodegradable, non-bio-based and biodegradable. So there are a lot of definitions. But the thing is that biodegradable bioplastics are only biodegradable under specific conditions and not in the environment. We performed experiments using soil collected from greenhouses or from fields planted with olive trees, and we exposed them in the greenhouse that we have, and we added many types of bioplastics, PLA, PHP, thermoplastic starch, BioP, and many others. And we also used the real mulch films, a commercial one that farmers have the option to use instead of polyethylene films. But in all cases, and this was very disappointing, we did not see significant weight reduction after more than 200 days of exposure for virgin pellets. And for mulch film also, we did not see any significant deterioration when we added them in the soil microcosms. So I don't know if the solution is, and also we measured the enzymes, the soil enzymes related to cycles, so carbon and nitrogen cycles, and there was an effect due to the presence of biodegradable plastics. So according to our experiments, but I've seen that there's a growing literature that support this, that biodegradable plastics are not biodegradable in everywhere. So we need to be very careful about the term biodegradability and about promoting this transition from plastics to bioplastics, because we also, according to our experiments in marine environment, the bioplastics produce a huge amount of micro and nanoplastics. And I know that papers that support that bioplastics can induce toxic effects to microorganisms similar to conventional plastics. So I don't know the solution. I think But for sure, replacing conventional plastics with biodegradable mulch films, it's not a solution that guarantees a plastic-free soil environment.
Thank you very much, Evie, for the answer.
Hello, I have also a question for Mariana this time. I'm not sure, maybe you said it already, but I'm not sure if I got it. I saw this percentage that you saw previously for the crystallinity of polymers, and it was reducing when I'm not sure what happened there with the crystallinity, and I want to, because it seemed to me quite interesting as an index for how rigid the plastic it is. So I would like maybe some more information about that. And maybe a more general question for maybe all of us, because I saw that, and I know that this research that we all do in plastics is quite new, and it's really depending on fundings, on European fundings or national fundings, and it's kind of a political also aspect to give money and to give space to this new research. And at the same time, I saw 2 days ago that the new president of the United States took back the ban of plastic straws, just like this. So I'm just curious, and I'm wondering if you think that this will affect our research. I mean, all these changes maybe can affect us, and maybe we do less research, or just thoughts about this. Thank you. Yeah, maybe you can go there.
Yeah. Okay, thank you. So regarding the first question, so we evaluated the crystallinity of the 3 polymers. I only showed the results for polyethylene with this technique called X-ray diffraction. This was a work actually that was done in collaboration. This was actually an analysis that was done in collaboration with another institute, so I didn't do this analysis myself, but I can give you information on how it was done. So yeah, it was done with this technique that I mentioned, and then you obtain this data that is kind of like a spectra, and you need to divide that into the area that is amorphous, which is like below a peak, and then the peaks are the crystalline peaks for that polymer. So we first need to do some processing of the data to separate this. And then based on that, you can calculate this percentage, show how much area corresponds to these crystalline peaks and how much area corresponds to the amorphous components. So after doing that for all the samples, we indeed saw some changes. For some of them, it was very minor changes that we say there was no significant modification of the crystallinity of the polymer. However, what I showed was that for polyethylene was the ones that were exposed to solar radiation and also to the weathering, that there was an increase of this crystallinity. And when I looked also into the literature, there was many different reports. So there were some studies that said that with the exposure and with the degradation, you actually get an increase in crystallinity. Other studies were saying that you get a decrease. So it was not very clear what you expect to happen. So it's a more difficult indicator, I would say, to use. However, we were trying to look into something that was a bit different. So yeah, it was a bit novel to me as well, but I think it was interesting. And again, as I mentioned, we were doing all these characterizations because then when we performed the sorption experiments, when we had, for example, one contaminant that was being absorbed and another one that was not, then we could try to explain a bit due to these different characteristics of the polymers when you compare the degraded one versus the pristine version of it. So regarding the second question, that's a bit more difficult question. I would say that even if the politicians come back with some regulations, I think as citizens, we always have important play in this. And I would say that a lot of people now are much more conscious about the plastic pollution problem. And even, for example, if some brands start to decide to return back with the plastic straws, we still can create some pressure on that and avoid, for example, using these brands. And this is something that the companies don't want. So I'm not entirely sure if, for example, a brand like McDonald's, let's say, will come back to the plastic straws, because then people can start saying, well, I'm not going to use this brand because they are returning back on this. So we will see how this evolves. For me, it's not very clear at this point what will be the results on this. Of course, we can have, again, an increase of the plastic straws, but it can actually stay mostly the same as it was because, again, we have the last say, let's say, on if these straws are used or not.
Yeah, I just wanted to say that I think it's gonna be very, very relevant for the plastic treaty negotiations, the new elections of the presidents of the United States, because my fear, I'm a bit more pessimistic than Mariana, but because I mean, as you probably know, the International Plastic Treaty was not ratified. There is supposed to be this year another INC where all countries, United Nations, should meet and try to ratify this treaty. But the negotiation failed because there were some countries that didn't agree on reducing plastic production and pollution. And I think right now, probably the United States will not ratify this treaty. I'm actually quite sure that they will not ratify this treaty with the new presidency. Which, I mean, we already saw this happening for carbon dioxide. United States never ratified the Kyoto Protocol, so they never agreed on reducing carbon dioxide emissions. So even though the last government made politics in that direction, these United Nations treaties were never ratified, and so they will not be ratified this time. And so I think nothing is going to change for a long time. This is my pessimistic view, but yeah.
Giuseppe, I wanted to ask you, since you put it so nicely about the reluctance of the politicians or the governments to do something. As a scientist, I mean, how reluctant are we to impose the protocols you mentioned? Because you mentioned so many protocols and and so many things that they can go wrong, from planning a sampling technique to analyzing it. So are we? I mean, what do you think is the major obstacle to have a common protocol in Mediterranean? I know it's many, but if you can pick the top one.
Protocols with the marine strategy. So all European countries are now already monitoring plastic in their seas, on their beaches, with harmonized protocols. The problem is that these protocols are not ideal. As I said, they are not really, I mean, we all use the same, so we all have, this is good, they are comparable between different countries, maybe. As I said, for instance, if everyone is doing visual sorting, then it really depends on the person that is counting the particle, right? So, but the protocols are harmonized, at least for the European policy right now. The work we are trying to do is to improve this protocol so that they are more reproducible, because I don't think it's too difficult to agree on a common protocol. We have many protocols available. We just have to choose one, and everybody agrees to use that one. The problem is that one is probably not reproducible. So it can be harmonized, but it's not standardized.
So I see there are no more questions at the audience here, no more questions at the chat. Well, thank you all for being here. I would like to thank also Giuseppe, Marianna, and Andrea from traveling from their countries to be present here at the event. Thank you very much. And for being part of the Harm-Plast. I want to thank Dana and Nicoletta for presenting. And also I want to thank the Evie, Theodora, and Win for being online and presenting. And of course, I want to thank ATMR for hosting the event today and supporting financially. And of course, Euromarine for giving the chance for early career researchers to apply for grant and funding the whole Harm-Plast project, paying for the expenses for the 3 researchers to visit us and support mini projects right from early career researchers. This can be also part of the answer, Nicoletta, that you said about fundings. It's good that there are still foundations giving some fundings. I don't know if this will be altered with a new president, but we are lucky we had the chance to have the grant from the Euromarine. So thank you very much for having been here and for making it Harm-Plast workshop being a very, I guess, insightful for all of us. Thank you very much.